Hi, thanks for watching this screencast. Today we're going to talk about the hydrologic cycle, also known as the water cycle. So let's just start with this. As humans, we rely on fresh water. We drink it, we water our crops with it. Without it, there really wouldn't be life on land. There would only be life in the water. And if we look at the distribution of the world's water, what we notice is this: 97% of the water on the planet is salt water. It's in the oceans. It's fine for marine organisms, but not for terrestrial organisms like you and I. So there's just 3% of the water on the planet that's fresh water that's consumable by land-based organisms. But now look at this. Of this 3%, almost 80% of it is trapped in glaciers and really isn't available anyway. That just leaves this small amount, like 20% of 3%, that's available to all life on land. And so obviously that's a pretty precious resource. And quite frankly, in your lifetimes, there will probably be wars fought over this resource because it's becoming more and more difficult to come by. So for that reason, we ought to learn about this hydrologic cycle. So the hydrologic cycle involves the movement of water primarily out of the ocean, where 97% of it is, and then up and onto land, where it provides fresh water for living organisms. And then it flows back into the ocean. So it's a cycle. And this cycle is powered entirely by energy from the sun. The sun is what makes water evaporate. It's what makes convection currents that make winds that can carry that water, wet, moist air over the land, where it can then return that water to the ground. So let's look at the steps in this hydrologic cycle. So it starts with evaporation, also something called transpiration. We'll get to that. It's followed by condensation, precipitation, runoff, infiltration, and groundwater flow. So those are the parts of the hydrologic cycle. We're going to take each of them in turn. Let's start with evaporation. So when the sun shines on a water surface, and what I think 70% of the world's surface is covered by water. So when the sun shines on, say, the ocean, water molecules at the surface get heated and they go from a liquid state into a vapor state. That's all that we mean by evaporation. It is a transition from a liquid state to a vapor state. It happens because of solar energy being absorbed, and it happens primarily on the oceans, but also in rivers, lakes, from the soil, and so on. Transpiration is a fairly significant component of the hydrologic cycle that is caused by the actions of plants. So plants undergo photosynthesis. They also just have unused water that they bring up through their roots. And this water essentially evaporates off their leaves, if you will, or photosynthesis breathes it out. And so what we find is there's quite a bit of moisture leaving, water vapor leaving plants. And we call that water vapor that leaves the ground through the action of plants transpiration. Plants transpire the water. Now, as water vapor moves upward with convection, then what happens is, we've talked about this before, adiabatic cooling cools it down 7 degrees per kilometer. So as it goes up, it gets colder and colder and colder until the moisture condenses into little tiny droplets. And these little tiny droplets are small enough they can be held aloft by the movement of air molecules, and they form clouds. And so we call that process of cloud formation condensation. Now, if these droplets in a cloud continue to grow, as they will, then eventually they get so heavy that the movement of air molecules can no longer hold them aloft, and then they fall out of the air. And they typically fall out of the air as either rain or snow. And when that happens, we refer to it as precipitation. And there's many forms of precipitation, but as far as this course is concerned, all we really care about is the fact that when water gets up into the air, it condenses, and after a while, condensation makes particles so large they can't stay up anymore, and that brings it back down to the ground, where it is now available to terrestrial life forms. Now, the thing is, remember, we get convection currents, right? So air tends to circulate, and sometimes it moves from the land out to sea, but a lot of times it moves from the sea over to the land. And when that happens, it takes water out of the ocean, brings it up, condenses it, carries it over the land, and then it rains there on the land. Without the energy from the sun to do this, there wouldn't be any life on land. Now, what happens when this water lands on the ground? Well, there's two things that can happen, just two. One is it can infiltrate into the soil. And what that means is these water molecules, under the pull of gravity, will start sinking down between the pore spaces, the openings between mineral particles in the soil, and they'll work their way down into the ground. We call that infiltration. They are infiltrating the ground. But this takes time. And if water isn't able to do that, then it will flow horizontally across the ground in what we call surface runoff. So basically, there's two options when the water lands on the ground. It can either infiltrate into the soil, or travel horizontally across the soil as runoff. Now, infiltration involves moving downward through these pores. It takes time, and because it takes time, if the rate of precipitation is too fast or the ground is tilted too much, then before the water molecules have a chance to get into the ground, they'll flow horizontally across as runoff. And runoff is something we typically have a negative view of. I mean, it is a natural process, but humans tend to make it happen a lot more than it needs to. And here are the problems associated with runoff. So when it runs horizontally, it moves into lakes and rivers, which is fine. But you notice here, it's carrying sediment with it, right? So there's some problems associated with runoff. All right, namely this: if it happens too fast. So if a lot of water lands on the ground and it doesn't go into soil, then it ends up in rivers. And when a lot of water ends up in rivers, we have floods, and so clearly that causes a lot of human life loss. The other thing is, as it flows horizontally across the ground, it tends to drag soil particles with it. And these soil particles also contain a lot of nutrients, right? So it carries this soil away and into the water streams and lakes. Well, that problem there is, without soil, you can't have crops, and people need to eat. So we don't want to lose the soil through erosion, but we do. And the other thing is, because these soils contain nutrients, when these nutrients get into our streams and lakes, they cause algae blooms, which cause a whole host of problems. So the three things: flooding, erosion, and nutrient transfer. These are the problems associated with runoff. And humans are notorious for causing increases in runoff through our actions, which we'll talk about in a minute. Infiltration then is beneficial. And we have generally runoff bad, infiltration good. Okay, because here's why: it prevents flooding. So every water molecule that goes into the ground did not end up in your stream, at least not initially. So it rained, but you didn't flood. That's what we want. It also a lot of it gets stuck to these soil particles, and so it provides the soil moisture on which these trees are going to grow the remainder of the year. So terrestrial plants, which are the basis of all life on land, are totally reliant on soils and soils having water in them. The other thing that happens is, a lot of times there are contaminants, whether bacterial or chemical contaminants, oils, pesticides, whatever. These things tend to stick to soil particles as the water goes down. So this process of infiltration acts as this wonderful water filter. So water that comes out of the ground tends to be very, very pure water compared to water that's found in streams. And the other thing is that as this water moves in, it's going to recharge underground water sources, which we're calling aquifers. More on that later. So, so here's what determines whether or not we're going to get infiltration or runoff. All right. So basically, the things that lead to runoff are steep terrain. So when water lands on a steep surface, it starts flowing right away. There's a greater force causing it to accelerate downhill. So you're less likely to get infiltration when the ground is steep. The rate of precipitation is huge. If rain comes down slowly, then water has a chance to get into the soil. But if it comes down quickly, water tends to build up on the surface, waiting for the water molecules below it to get into the soil, and they're not going to wait. They're just going to slide off. So fast rain, heavy rain, that tends to cause increased rates of runoff. Another one, and this is something that humans are responsible for, is a lack of vegetation. When we clear the trees and shrubberies off of hillsides, then water ends up getting to the ground faster. If you've ever been stuck in a rainstorm and you were outside and didn't have an umbrella, chances are you went under a tree, because being under a tree, the water sticks to the surfaces of trees, to the leaves and the trunks. And so it reduces the rate at which it reaches the ground. And so that gives the water a chance to infiltrate. So if you take the trees away, you're going to get less infiltration and more runoff. And finally, humans have a tendency to put a lot of what we call impervious surfaces through which water can simply not infiltrate. I'm talking cement, asphalt, roofing materials. So what causes infiltration to occur? Well, gentle slopes, the presence of vegetation, rainfall that isn't too heavy, and soil that is porous rather than compacted or covered with impermeable surface. So those are the two things that are that you either get runoff or you get infiltration, and it really has to do with those factors. Now, as I said, trees are very important because they slow down the rate at which the water reaches the ground. Even in a heavy rain, they slow it down and give the water a chance to infiltrate. But humans have this awful tendency to chop down trees and clear away land, either uh, to sell as timber, to grow crops, or to make way for human housing. So humans are notorious for doing that. And each one of these activities, when we take away the trees, we increase runoff and all the problems associated with runoff. Also, when we build urban areas, we tend to put down impervious surfaces, concrete, asphalt, roofing, and that basically totally prevents water from infiltrating. And so it has to go into our surface streams at that point, and it tends to be responsible for a lot of flooding and the movement of contaminants from our street surfaces, oil from cars, feces from dogs, and it moves it into streams. Now let's just talk about like what happens when water goes into the ground. Okay, let's focus now a little bit on infiltration. So as water infiltrates the soil, it moves downwards, right? Infiltration means the downward movement. But basically what we have is this. The upper layer of the soil is what we call the unsaturated zone. Sometimes we hear it called the zone of aeration. Basically what this means is this. If we took a close look at the soil particles here or the rock particles here, what we're going to notice is the pore spaces between the mineral grains are mostly filled with air. There'll be little water molecules adhering to the surface, but the pores themselves are full of air. But if you keep moving down, water's got to go somewhere, and eventually you get to the point where the pores are saturated with water. There's no more air to be had. It's all been taken up by water, so we call that the saturated zone. So basically, water infiltrates through the unsaturated zone, moving between these pores, and then it reaches the saturated zone, and it can't do that anymore. So what happens is when it reaches the saturated zone, instead of moving downwards as it did through the unsaturated zone, it tends to move downhill still, but parallel to the land surface. And that's what we find when we get into the saturated zone. Now, the water table is a term we use to refer to the boundary between these two zones. Infiltration happens as water moves down through the unsaturated zone, and the water moves parallel to the ground surface when we get into the saturated zone. And the boundary between these two is called the water table. And we'll find this water table can move up and down depending on rates of infiltration and flow out of the saturated zone. So the water that gets into the saturated zone is referred to as groundwater. So when water is moving downward through the unsaturated zone, we don't call it groundwater. But when we get to this saturated zone where the water is flowing horizontally to basically is paralleling the land surface, right? We refer to that as groundwater. Now, where does this groundwater go? It is flowing. It's not flowing very fast, maybe like a few centimeters a day, but it's flowing. So where does it flow? Well, it flows to the same place that surface runoff would. Surface runoff would carry this water downhill to, say, a lake or a stream in a matter of hours. Okay, but once it gets into the groundwater, it can take many years. But it's going to end up in the same place. It's going to end up flowing out through springs and into rivers, and we call that discharge. Okay, so an aquifer is a body of underground rock that is porous, and those pores are filled with water. It is the rock that contains the zone of saturation. We call this an aquifer. And the purpose, the value of aquifers is they are a reservoir of water, of clean water that humans have access to. So think of it this way: water is flowing. Groundwater is always flowing. Okay, so an aquifer is in motion. And so, it's a finite thing. So if it just kept flowing out, it'd run out. Well, what happens is infiltration recharges the aquifer, and the flow of groundwater tends to discharge it. And where does it discharge to? Well, it tends to discharge into streams, lakes, the ocean, or through human action by pumping. We like to pump water out and put it in your house or put it on our crops. And so when humans put wells into aquifers, which we do all the time, we increase the rate at which that aquifer discharges. And unfortunately, we also have a tendency to decrease the rate at which infiltration recharges aquifers by this process we talked about before, which increase the rate of runoff. Now let's look at this diagram. It just gives you an idea of the saturated zone, the unsaturated zone of the water table. So what happens is this: during the rainy season. Now, in many parts of the world, the rainy season is the summer season. I know here it's the opposite, but let's just say the rainy season. In the rainy season, the rate of infiltration is going to cause the aquifer to recharge at a faster rate than which the flow of that groundwater will cause it to discharge, say, to a river. So because of that, the aquifer is building capacity. So it gets higher and higher and higher. And we find the water table moves up during the rainy season, which in most of the world is the winter season. Then in the dry season, the rate of infiltration is decreased. So recharge is decreased, but the rate of discharge through groundwater flow stays constant. So what happens is the water table tends to drop in the summer. And there's many places in the world, like say the American Southeast, really all over the place, where you have streams that only run during the wet months because the water table is above the surface, feeding them, discharging into them. But then you get into the drier months and uh, the aquifer is below the river level, so the river just goes dry. Now, humans pump a lot of water out of the ground, and there's certain places where aquifers have a difficult time recharging because the rate of infiltration is low because precipitation is low. I'm thinking California, Arizona, in America, all over the world, right? All over the Middle East, all over Africa. It's everywhere, okay? And what happens is if you pump water out of the ground, causing the aquifer to discharge at a higher rate than it can recharge through infiltration, then the aquifer is going to become depleted. It means it's going to run out, just like a battery becomes depleted of charge if you discharge it faster than you recharge it. It's just like a battery, okay? And so look at this. Uh, Here is a place in California where this person is trying to show just how bad this is because it can actually cause the land to sink down. It's called subsidence, and it just illustrates just how dramatic this aquifer depletion can be. So in 1988, this is where this part of California's Central Valley was located. And since between 1988 and this picture was taken in 2013, and believe me, it's gotten much worse since then because of their drought. Just in that time, it had dropped like over a meter and a half. So we call this basically land substance is caused by aquifer depletion, and eventually these aquifers become completely depleted, and then you don't have access to that water, and all the crops you were watering with it no longer have a source of water to be watered, and then all the humans that relied on that food now don't have that food. So you can see how this is a problem, and it's a looming problem because all around the world aquifers are becoming depleted because humans are just pumping that water out. And the last thing I'll talk about is this. In coastal areas, normally what happens is the flow of groundwater is such that instead of discharging into a stream, it discharges into the ocean. That fresh water just flows out into the ocean and discharges there. But what happens is when people put wells, pumping wells, in areas of a coastal aquifer and we start pumping water very fast, instead of the aquifer becoming depleted like it would, say, in the Central Valley, instead it starts to flow the wrong way. And salt water starts to recharge the aquifer. So we get this flow of salt water in. And normally the fresh water would be flowing out, but now the salt water is flowing in, and all of a sudden your well becomes salty and you can't drink it. Things that live on land can't use salty water. Not humans, not plants, anything. And the worst thing is, if I just shut off this well and say, whoa, I'll just shut it off and wait for this situation to turn back into this situation, unfortunately, the salt that got in by this process doesn't leave very easily. And even a human lifetime may not be enough time for this saltwater intrusion, as we call it, to allow this well to become usable again. Hey, listen, thanks for watching this. This is a lot of information, and I want to spend the whole period practicing. That's why I'm asking you to watch this screencast. So I apologize for intruding on your home time, but thank you for watching.